Hello everybody, we welcome you all. Here we present the optimization plugin for RapidMiner. This plugin was developed in the Collaborative Research Center SFB 876 as a part of Project C1. Optimization is nothing but finding the best value among available choices. Here we will define an unconstrained optimization problem. The aim of the unconstrained optimization problem is to minimize the objective function. That is, to be more specific, to find the value of theta which minimizes the value of the objective function j here. Here x is the training data set and theta is the weight vector or the learning variables of the optimization problem. So why do we care? Optimization is already in the heart of many machine learning algorithms. Linear regression, which minimizes the squared error, and logistic regression, which minimizes the logistic loss, are a class of unconstrained optimization problems. Similarly, many other machine learning algorithms such as k-means, collaborative filtering, and support vector machines can also be expressed as optimization problems. So what does optimization plugin for RapidMiner has got to offer? It implements several iterative optimization algorithms. These are a class of algorithms where we start with zero vector for the learning variables or the weight vector and update them in each iteration such that the new value of the weight vector reduces the value of the objective function. The way the weight vector is updated differs from algorithm to algorithm. These iterations are repeated until convergence or specified number of iterations. So the optimization plugin for RapidMiner introduces mathematical optimization based learning capability to the RapidMiner and also provides a configurable optimization based learner to the user. Here we briefly describe the features supported by the plugin. Both smooth and non-smooth problems are supported. Smooth problems are problems which are designed to solve smooth objective functions, and non-smooth problems are problems which are designed to solve non-smooth objective functions. Here the smoothness refers to the fact whether the objective function is differentiable and continuous. Plugin also supports various cost functions such as least squares, logistic loss, and hinge loss. There is also support for line search, which is again optimization subproblem of finding the optimal learning rate for each iteration. First order methods, which are based on the gradients such as gradient descent, stochastic gradient descent, and second order methods which are based on the Hessian matrix or second order derivatives such as Newton, are also available in the plugin. Batch algorithms such as gradient descent and online algorithms such as stochastic gradient descent, dual regularized averaging are also part of the plugin. Plugin also supports various regularizers such as L1, L2, elastic net, and group L1. The plugin features the implementation of dual regularized averaging, which is capable of finding highly sparse solutions in high dimensions. Plugin contains a sample repository which contains sample data and processes. The sample data is from the popular MNIST dataset and the wine quality dataset from the UCI machine learning repository. So what we see here is a sample process from the sample repository. The optimization plugin introduces only one learner called OptimLearner. All the features mentioned earlier that are offered by the plugin are configurable as parameters. So for example, the problem type or the optimization algorithm, loss function, an option to predefine the number of iterations, and the type of regularizer, and the parameters for regularization constants, and the line search types. The line search is available only for smooth optimization. And when we switch to non-smooth optimization, the options available for the optimization algorithms and the loss functions and the regularizers are changed dramatically, so that only valid choices are presented to the user. The plugin also supports a real-time convergence plot which displays the value of objective function over each iteration and the relative change in the objective function value. In this sample process, we learn from the training set and evaluate the performance of the model over the test set. Here we adjust the parameters so that we now run a smooth problem type using gradient descent, and the number of iterations we set it to 5, and I'm choosing the logistic regression as a cost function with L2 as the regularizer. I'm giving the regularization constant L2 to 0.001, and I'm choosing the line search as Armijo, and you can leave the parameters to default when you don't know how exactly to tune them. So I'm running the sample process now. So you can now see a convergence plot has popped up. Now the process is completed. You can see from the performance that it has almost predicted all the classes correctly. And let's see the convergence plot. As you see here, you can see that the objective function value is decreasing for each iteration. Next, we present some results from the experiments done using the plugin. Here we compare smooth and non-smooth algorithm being applied to a non-smooth problem. By non-smooth problem, what we mean is the loss function is non-smooth. Here the loss function used is hinge loss and the data set used is MNIST, and we use the L2 regularization. As you can see from the performance metrics here, SGD, which is a non-smooth algorithm, performs better on the non-smooth problem than that of gradient descent, which is a smooth problem. We will also compare the graphs now. As you can see here, the relative change of the objective value in case of gradient descent is very shaky. In case of gradient descent, it just takes the subgradient of the hinge loss and proceeds, and in case of subgradients for a non-smooth function, there is no guarantee that it will decrease the value of the objective function. Whereas in case of SGD, we can see that the algorithm converges faster with the increase in the number of examples that that has been processed. Next we see the comparison between batch and online method. The batch method uses information from all the examples in each iteration. Gradient descent is such a method, whereas the online method such as stochastic gradient descent or regularized dual averaging use only one example for each iteration. Here we can see both of them have same level of accuracy. Gradient descent converges slowly on each iteration. There is a decrease in objective value, and close to iteration number 35 it converged. And we have to keep in mind, in each iteration it processed all the examples, whereas stochastic gradient descent converged very soon, even with 250 examples or so, even before 250 examples. Next we compare regularized versus non-regularized methods. Here we showcase the performance of L1 regularized dual averaging algorithm. Here lambda is a L1 regularization parameter or constant. The x-axis in the graph is the L1 regularization parameter value, and we can see that the accuracy decreases with increase in lambda, but the amount of sparsity in the solution is highly beneficial. By sparsity we mean that the number of non-zeros in the weight vector drastically decreases with increase in regularization constant, with increase in value of the regularization constant L1. So this is a highly attractive method which can be used with high dimensional data. This is capable of finding solutions in a lower manifold than that of the actual dimension space. Next we compare the performance of the plugin with Weka and existing RapidMiner operators. We compare the performance of algorithms such as gradient descent, stochastic gradient descent, RDA, with RapidMiner's logistic regression and Weka's logistic regression and stochastic gradient descent. As we can see from the results, the optimization plugin outperforms both Weka and existing RM operators in terms of speed as well as accuracy most of the times. And it also offers a new type of learner called regularized dual averaging based learner, which is capable of finding sparse solutions in high dimensional space. Here we presented a configurable optimization based learner for RapidMiner. This plugin also offers the optimization algorithms as libraries which can be easily extended and used for solving other type of machine learning problems. Thank you.